Okay, so we continue with section 1.5. And here I want to talk about some very basic definitions related to groups. Namely, I will talk about order and subgroups and isomorphism. Just first things one can talk about when you just see a group. So let G be a group, and then order of G is the number of elements in G. So notation is usually this G in these brackets, and so of course it can be just a positive integer, so maybe n, or it can be infinity, but also it's a bit misleading. So if you know what is the cardinality of a set, so number of elements is usually called cardinality of a set, and infinity being not finite, actually it's not true that between two infinite sets there is always a bijection. There are types of these infinities. So for instance, G can be countable, uncountable, of cardinality continuum, or bigger, and that's all the standard questions of sizes of sets as they start to play a role here. But maybe we will mostly distinguish between finite, so this is the case when a group is finite, then when G is in bijection with basically Z, it will be called countable, so you can just label all the elements, and otherwise uncountable. But so if you know all these countable, uncountable sets and so on, then just apply it to G as a set. If you don't know, you can skip it. That's not terribly important right now, but that's a beautiful topic to look at. So, and then we had, for instance, this cardinality of Sn equals n factorial, the fact we discussed, and cardinality of Z over Nz equals to n. And cardinality, so Z is countable, but R is not. A huge part of this course will be about finite groups. So these guys are called finite when the set is finite, and we will mostly discuss them just because we are able to prove a lot of things in this case. But later on we will also talk about other examples. Okay, so next question is, let's just look at one element in a group. So first I want to make a remark about degrees. So what? Let G in G is an element. So then define G power k being just G times G k times, of course. So for k being positive integer. So then G power 0 can be naturally defined as the identity element. So in any group, it's this one. Notice that, we'll talk about G power minus k is, of course, G inverse times G inverse times and so on times G inverse, and that's the same as G inverse power k. So all usual properties you learned at elementary school of powers, like G power n power m is G power nm, for g power n times g power m, g power n plus m, all of them are true in any group. So that's all very simple. And also maybe just a remark is that so in Z, for instance, so if you take some number n power k, that's actually, so in group theory notation, it's actually n plus n k times. So one should be slightly careful that this additive and multiplicative notation can get into a clash. For instance, here. So for abelian groups, that's very typical. For non-abelian groups, people would never use plus, I guess, I hope. Okay, so then I want to say what is an order of an element. So an order of G is the smallest k in n such that g power k equals to e. So when you multiply g, at some moment you will get e, and then so basically you have identity g squared, and so on, g power k minus 1, and then you have again identity, and when you multiply, you take power k plus 1, you will get g, and so on, and so you have a cycle. So kind of, if such number exists, then you have a cycle. So let me say if it exists. So if it does not exist, order of G is infinite. So the notation is usually ord of G, and that's a positive integer or maybe infinity. So in Z, for instance, in Z, order of 0 is infinity. Oh, sorry, is 1, and order of k is infinity for k not equal to 0. But for instance, we can take, say, z over 10z, and that's an interesting example related to this last digit. And so we get that there are 10 elements, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And I can write down their orders here. So this one has order 1. 1 has order 10. So if you multiply 1 on 2, on 3, on 4, you will get different last digits, obviously. So 2 has order 5. So 2, 4, 6, 8 are all different. 10 is the same as 0. And so 2 power 5 is 2 times 5 is 10 is 0. So that's why it has order 5. So one can check that 3 has order 10, 4 has order 5, 5 has order 2 because 5 plus 5 is already 0, 6 has order 5, 7 has order 10, 8 has order 5, 9 has order 10. So you see some interesting numbers appear. And it's a fundamental fact that all of them divide the order of the group. So 10 is divisible by 1, 10, 5, and exactly these numbers we see here. And that's a general fact which we'll prove in the next section. So also we'll see that all these elements up to the order -1 are all distinct. The proof is very simple. If 2 of them are the same, so maybe let me just say, so these elements, these are distinct. So we will maybe reprove it again when we talk about this so-called cyclic groups, these groups generated by one element, but the proof is just basically you say g power a equals to g power a plus s, and then you can use cancellation property. You conclude that 1 equals to g power s, and so a smaller power of g is equal to 1, and so it's this number k minus 1 was not the smallest. You can use this logic. So we will do it, but I'm just maybe briefly describing that. So one of homework problems is to find orders of all elements in S3. That's very simple. So understanding all orders of elements in Sn is harder, but we will talk about that. That's also very doable. It's an interesting problem. Okay, so this what about order. So next we move to subgroups, and after that to isomorphism. Okay, next I want to talk about subgroups. So definition. So G is a group. H is a subset of G, is a subgroup if it is closed under product. So for every element H1, H2 in H, if you take two elements in H, they're also in G, so we can multiply them. H1, H2 is supposed to be in H. A priori, it might go away. That's called closed. So second one is identity is in H. And third, for every element H in H, the inverse is in H. Again, the inverse exists in G, but a priori might go away. So this is the definition. But what it actually means, it just means you want to look at a group and you want to have a subset, which also is a group, so kind of smaller group. Maybe these are symmetries of isocahedron, and these are symmetries of isocahedron preserving, I don't know, sending something to something, fixing some diagonal, fixing some vertex, or anything like that. So basically a subgroup is just a subset, which is also a group, and operation in H and operation in G are matched. So when you multiply two elements in H, it's the same as multiplication in G, and the same is true like for identity in H is the same as in G, and inverse in H is the same as in G. So that's just kind of you combine the notion of a subset plus a notion of a group. You want a subset to be a group with the same operation. And indeed, so this is so proposition is that H with H1 times H2 being, and then this is a like weird way to write it, but what I will write is like multiplication as in G, identity E being the identity as in G, and is a group. So, and the reason is very simple, because if you look through group axioms, so there are three axioms. First of them is associativity. But actually first of them is that this map product exists, and closeness just tells you that, okay, you can multiply elements in this way. You indeed get a map from H times H to H. So that's a priori not obvious, because it might happen you go outside, and this just, you want this element to be in H. So then associativity is obvious, because it's true for every three elements in G. Certainly it's true for every three elements in H, even more true. So identity is existence property. It should exist, and it might be outside, so we want it to be in H. And then the inverse, we want every inverse of every element again to be in H, so that basically the proof of this proposition is totally obvious. Nothing to prove. And also I want to give you a couple of exercises. So exercise, I used some fancy way of giving you exercises. So like this. Exercise, I want to give you two here. So again, exercises are not kind of homework problems, they are not graded or anything, but I strongly recommend you solve them. It should take like less than a minute for each, or 30 seconds. So H1, H2 are subgroups of G, then their intersection is a subgroup. Actually, more is true, just if you intersect any number of elements, any number of subgroups, maybe finitely many, maybe uncountably many, doesn't matter, you will still get a subgroup. That's one exercise, and another maybe, so for any group G, G and just a subset containing just one are subgroups of G. So also we need some notation. So notation is something like this, so less or equal. It's kind of like a subset, but just less or equal. And that's the notation. Okay. So, and as usual, there is a confusion. So if people just write this, some means that it's a subgroup not equal to G, and some means that actually this is the same. So, and honestly, I don't even know what I will do. I will try to stick to this one. And I will say explicitly like not equal if I want it not to be equal. Okay, so some examples. So, examples. Okay, so for instance, Z, G can be equal to Z, and H can be equal to even numbers. So, and we need just checks, okay, sum of even is even, 0 is even, if n is even, minus n is even, that's it. So another example can be G can be Z over 10Z, and H can consist of two elements, 0 and 5. And again, first we check, okay, 0 plus 0 is 0, 0 plus 5 is 10 is 0, 5 plus 0 is 5, 5 plus 5 is 0. So it's closed, 0 is there, minus 5 is the same as 5, so it's also there. That's a subgroup. So 3 might be, let's take S6, S3. And okay, so these are just permutations of 3 elements. And for instance, one can take H to be a subgroup consisting of identity, 1, 2, 3, 2, 3, 1 permutation, 1, 2, 3, 3, 1, 2 permutation. And a priori it's not obvious it's a subgroup, you need to check something. But if you denote this element by G, you'll see that this is G squared, and this is an element of order 3, so G cubed will be back E. And so this is why it's easy to see if you multiply any of these elements, you will get some power of G, but actually only powers of G which you can take are 0 power, 1 power, 2, because G has order 3. So that's why it's closed. G inverse is G squared, and identity is there, so it's a subgroup. And if you remember, when we talked about a triangle, so we talked about a triangle, and there were, so S3 was group of symmetries of a triangle, so these were symmetries of a triangle. And inside this group of symmetries, there were 3 reflections and 3 rotations. And this is basically a rotation by 120 degrees, and this is a rotation by 240 degrees. And this subgroup actually has a meaning. These are those symmetries of a triangle which you can perform by just taking your plane as sort of a rigid object and like moving it. Because if you want to do a reflection, so other 3 elements are these symmetries, you need to actually get outside of your plane. So this will be called orientation preserving orientation preserving symmetries. But to explain exactly what that means, it will take some time, and I will talk about it, but later. Okay, so these are some examples of subgroups. Please solve the exercises. And now I want to go to the last topic of this section and discuss what is an isomorphism. And the idea is very simple. You have groups, and you want to know when two groups are the same. Because we have this feeling that, you know, some groups we have seen them already. So it looks like this one, for instance, H consisting of 0 and 5, where 5 plus 5 is 0. It's the same as this group with 2 elements where you had this flip. So it's just another instance of this flip group, and it should be, we should say they are equal. But, I mean, one of them is about remainders, another of them was a symmetry of a Christmas tree or something from first lecture, and in which sense they are equal. And of course, in the same sense, we say sets are equal. There is a map which identifies them. So we want them to be at least in a bijection, but this bijection should be definitely a bit special. So let me explain exactly what that means. Okay, finally, isomorphism. So this is a bit more complicated, but you're already familiar with isomorphism of vector spaces, so it should be fine. So definition. So I want to say two groups are equal. So let G1, G2 be groups. So a map F. So map is the same as function, so it's just F from G1 to G2. Is an isomorphism if first f of G1, G2 equals to f of G1, f of G2. So f, for every G1, G2 in the first group. So here multiplication happens in G1. Here multiplication happens in G2. A map F is an isomorphism if it takes elements in G1 to elements in G2, and rule of multiplication behaves accordingly. You multiply two elements, you send them here, and you multiply here. It's the same thing as multiply them in G1 and then send it. So that's one property we want to hold. Second property is that F is a bijection. Okay, that's it. As simple as that. So let me immediately point out the following. So 1 and 2 imply that. So I said that F should have a meaning that G1 and G2 are the same, but you might ask, okay, but what about units? What about inverses? So it's easy to see that 1 and 2 implies that F of a unit, and I mean a unit in G1, is a unit in G2. So indeed, F of the unit is the same as F of the unit times the unit, just because unit is unit times unit, which is F of E times F of E, and we can apply cancellation property. So this is something times E equals F of E times E, so this implies that E equals F of E. Just here you should remember that's not the same E, that G2, that G1. That's a little exercise again, very simple one. So exercise is 1 and 2 implies that F of G inverse is F of G inverse. That's very simple. So basically I might have included these two things inside the definition, but you don't need to. That just follows. And we even don't need to use bijection. So, okay. So this is one exercise, and also a few more. So composition of isomorphisms is an isomorphism. That's just trivial, more or less. Composition of bijections is a bijection, and then you check that the formula works out. And you can see that inverse of an isomorphism is an isomorphism. So that's very simple. Okay, so I want to say two groups are equal. Existence of isomorphism means this equal. So definition is that G1 is isomorphic to G2 if there exists F from G1 to G2 such that F is an isomorphism. And notation is just this G1 and then double line G2. Okay, so if you have studied linear algebra, which you did, you know what is an isomorphism of vector spaces. It's a map which is a bijection, sends sum to sum, scalar, product to scalar, multiplication of scalar to multiplication of scalar. That's the same type of definition. Map from one to another, which is a bijection, sending product to product. Basically, if there exists an isomorphism between two groups, it's not necessarily unique. There can be many. That's very interesting topic. We will talk about it. But if it exists, it means you can sort of relabel elements of G1 and get G2. So if you see their multiplication tables, you can sort of match them, but you need to maybe relabel elements in G1 to get elements in G2. And with vector spaces of finite dimensions, there was a theorem that just all of them are isomorphic. Two vector spaces are isomorphic if you don't leave their dimension matches. Nothing like this is true for groups. So studying the number of groups of certain order up to isomorphism is extremely complicated problem. There is a homework problem that every group of order 2 is isomorphic to are isomorphic to each other. All groups of order 3 are isomorphic to each other. Obviously, all groups of order 1 are isomorphic to each other, but there are quite a few of groups of order 12 up to an isomorphism. And so in general, that's a complicated question. We will do a few instances, and we will pretty well understand all groups of order up to 60, I guess, in this course. But if you just write down a huge random number, it's not completely clear what is a number of groups of this order up to an isomorphism. So next, I want to give a few examples of these isomorphisms, and we just look at what we already discussed. So examples. So the first one will be, okay, so we discussed these two fundamental sources of groups, Z over NZ, like Z over 2Z, and Sn, and for instance, we can take S2. And the statement is that they are isomorphic. And that's a very simple statement. So here we have elements 0 and 1. Here we have elements E. Let me write them as permutations, I'm sorry. We can say 1, 2, 1, 2, 1, 2, 2, 1. And then we need a bijection, which sends identity to identity, so this has to go here, obviously, and then it's a bijection, so the second element has to go here. And we need to check a few statements, but basically what we need to check is that if we do the labeling in this way, multiplication tables will match. And indeed, if this is E and the other is G, then in both cases we will have this familiar G, G, E multiplication table. For both of them, if you use E as 0 or 1, 2, 1, 2 here, and G is the second element. That's very straightforward. So second example is that, remember, we had this G being S3, and it had a subgroup consisting of 3 permutations: 1, 2, 3, 1, 2, 3, 1, 2, 3, 2, 3, 1, 1, 2, 3, 3, 1, 2. And this was H. And we discussed it's a subgroup, and if this is E, this is G, this is G squared. But also we have another group which looks like that. We can take Z over 3Z with its 3 elements. So it has element 0, 1, and 2. And 2 is also 1 squared. Remember, square here is times 2. So it's 2 times 1. And so we kind of also see here sort of G squared. So that's why we can just send E to 0, G to 1, G squared to 2. And that's an isomorphism, it's a bijection, and then it's easy to see. So basically, just because if you know that it is E, this G squared, and G cubed is E, you can write down this multiplication table immediately, it will match. So that's why it's an isomorphism. But there is another one. One can also do this cross. One can take sort of G to 2, and then G squared will go to 2 times 2, which is 1. So that's another kind of option. And so this isomorphism exists and is not unique, but actually H is isomorphic to Z over 3Z. So one of the beautiful facts in a group theory, one can try to, so we have seen a lot of groups already, and probably the most interesting is Sn. So in some sense, Sn is the most interesting group, finite group, for the following reason. Every finite group is isomorphic to a subgroup of group Sn. So to every finite group, you can find a subgroup in certain huge permutation group, so that they will be isomorphic. Z over 3Z is isomorphic to a subgroup of a group of order 3. Permutations of 3 letters. Z over 4Z will be isomorphic to a subgroup of S4, and so on, for instance. And this is a theorem which you will see, it is the hardest kind of problem in this problem set for this week. So please try to think about it. We will discuss it during classes, Zoom classes, and it's very, very important one. And we will also come back to it later on. I will kind of maybe explain another way to think about it somewhere in maybe 2 weeks. Okay, so here we finish this section, and in the last section of this first week class sequence, we talk about our first theorem in group theory, namely weak version of Lagrange theorem.